Hello, my name is Sina Masnadi and I'm going to present ConcurrentHull, a fast parallel computing approach to the Convex Hull problem. I will first talk about the Convex Hull problem background, then I will explain how our approach works and I will show you its benchmarks. Finally, we will talk about the limitations and future works and we will conclude our presentation. The Convex Hull problem is finding the smallest polygon or polyhedron of a set of points so that all the other points are inside those points. So for a set of points P, their convex hull is denoted as CH of P in this paper. There are numerous approaches to solve the convex hull problem. For example, Graham scan is one of the well-known approaches for 2D points. Miller et al. In 1988 proposed an approach which works with n CPUs for n number of points. But because the number of CPUs were pretty high, the approach didn't get too much attention. Yurkiewicz et al. Created an algorithm which works on CUDA to solve the problem by pruning a lot of points that are not a part of the convex hull. Among the literature, there are three projects that have their code publicly available: QuickHull, GHull, and CUDA chain. QuickHull is one of the oldest ones that is available for CPU computation, and it is available for 2D and 3D points and higher dimensions. GHull works on GPU and it works for 3D points, and CUDA chain works on GPU and it's for 2D points. Now let's look at how our approach works. This is a high-level presentation of the 2D concurrent Hull algorithm. In the first step, we load the data and partition them using a k-by-k grid. After partitioning the points, we will use crawlers to find valid partition and remove invalid partitions. We will talk about the crawlers in the next slide. A valid partition is a partition that we assume there might be a point inside it that is a part of our final convex hull. And an invalid partition is a partition that we are sure that none of the points inside it would be a part of the final convex hull. After finding the valid partitions, we will find the convex hull of the points inside each of these partitions and remove the points that are inside those convex hulls. After all of these prunings are done, we will find the convex hull for the remaining points, which is the convex hull of the input problem. I mentioned crawlers in the last slide, so what are crawlers? A crawler is a small piece of code that crawls over the partitions grid to find valid partitions. Each crawler has a starting point and a direction, and it starts from the starting point and crawls toward that direction. It will crawl until it finds a partition that is non-empty. Then it will mark that partition as a valid partition and halts its operation. There are 12 by k-2 plus 4 crawlers for each grid of k by k. Because we have k-2 two starting points for each side minus the corners, and for each of the middle partitions for each side we have 3 directions for crawling. And that would be 3 times 4 times k-2, and for each corner we have only one crawler that crawls diagonally. Now let's look at an example. So consider the blue partition as our starting point. For this starting point we have 3 crawlers, with 2 of them are diagonal and 1 of them is crawling toward the top of the grid. For the right crawler, we start from the starting point. Since that partition is empty, we will continue crawling. The next partition is also empty, so we have to crawl further. The next partition that the crawler encounters is not empty, so it will mark it as a valid partition and its operation will be halted. The next crawler crawls toward the top of the grid and it will keep crawling until it reaches the partition that is non-empty. So for this partition it will mark it as a valid partition and its operation will be halted. The next crawler also does the same thing and it will mark this partition as a valid partition and it will be also halted. So if we run the crawlers for all of the edge starting points, edge of the grid, we will have these valid partitions. We have covered the first half of the algorithm. So for the next half, after finding the valid partitions, we find the convex hulls for each partition independently in parallel, and then we will remove all the points that are inside those convex hulls, and we will run the convex hull algorithm for the remaining points, and we will have our final result. For the GPU part, it's going to be the same as the CPU algorithm. The only difference is that for the parts that is parallel, we have CUDA kernels that are responsible for those operations. So for example, after copying the data to the GPU memory, we will have n threads to assign the endpoints that we have to their according partition. The GPU crawlers also have the same principles of the CPU crawlers. Each of them are running in a separate thread. After finding the valid partitions, we have modified a CUDA chain algorithm to fit our needs to find the convex hull of the points. So we run CUDA chains on each valid partition in parallel, and then we will have the pruned points. We remove them and we will have the final points, and we use the CUDA chain again on those to find the final convex hull. The 3D algorithm works the same as the 2D algorithm with some small modifications. The crawlers in the 3D algorithm crawls toward 9 directions. So if we consider one of the partitions, the crawlers crawl toward all of the adjacent partitions in the next layer. So there are 9 partitions on the next layer, so we will have 9 crawlers. Here is an example for the 3D algorithm. We have a spherical point cloud. After loading the data, we will partition it into a grid. Then we will use crawlers to find the valid partitions. These are the valid partitions. Then we will remove the points that are inside the invalid partitions. The red points are those points. After removing them, we will have these points, which are the points that was in the valid partitions. We have to then find the convex hull of each valid partition and remove the points that are inside those convex hulls. The red points in the image shows those points that are inside those convex hulls. The total points that are removed using the algorithm are shown in red in this image. By removing them, we will have these blue points. We have to find the convex hull for these remaining points, which is going to be the final convex hull for the input data. Now let's see the benchmarks for the algorithms. For the 2D algorithm, we have 4 distributions of synthetic data. The first one is a square with a thickness of 1%, and then a square with uniform distribution, circle with a thickness of 1%, and a disk with a uniform distribution. For each of these distributions, we have a different number of points. This table shows the average of the performance on different distributions. As you can see, the performance of the ConcurrentHull is slower than QHull and CUDA chain for smaller datasets. But for larger number of points, ConcurrentHull starts to get faster. So for example, for 100 million points, ConcurrentHull is on average about 42 times faster than QHull. And for the 2D GPU algorithm for 100 million points, ConcurrentHull is on average 1.54 times faster than the CUDA chain performance. One interesting point about the ConcurrentHull is that for very large datasets, for example 1 billion points, both the CUDA chain and QHull algorithms faced out-of-memory problem, but ConcurrentHull could solve the problem for that large datasets. This plot shows the benchmark for the 2D synthetic data. The y-axis shows the time in seconds and the x-axis shows the number of points. Here you can see the effect of k on the performance of the algorithm for different distribution of points. All of these plots are for 100 million points. As you can see, increasing k will increase the performance, but after some point, increasing k will not affect the performance that much. To benchmark the 3D data, we generated some synthetic data, and we had 4 distributions. A cube with uniform distribution, ball with uniform distribution, sphere with thickness of 1%, and Gaussian distribution. This table shows the average performance time for number of points. Again, for a smaller number of points, ConcurrentHull is not faster than the other algorithms, but for large datasets, for example for 100 million points, ConcurrentHull is faster than the other algorithms. As you can see, for 100 million points, ConcurrentHull is on average 2 times faster than the QHull algorithm, and for 10 million points, ConcurrentHull is on average 8.3 times faster than ghull. We also had the out-of-memory issue with ghull and qhull, but ConcurrentHull could solve the problem for 1 billion and 100 million points. This plot shows the performance of benchmarks. You can see the effect of K for these 3D synthetic data. As you can see, increasing K will increase the performance, but in the case of the cube uniform distribution, increasing the K will increase the performance, but increasing it toward 30 will actually decrease the performance. We also tested the algorithm against some real-world data. We gathered some LiDAR scans from these websites and we tested the code against 4 different LiDAR scans. You can see the performance for the first dataset. As you can see, ConcurrentHull outperforms both ghull and qhull. You can see the outcomes for different datasets here in the plots. There are some limitations to our work. For example, finding the optimum size for K is one of the main limitations. We don't know what is the best number to choose for K. If we choose a large K, the performance will degrade because of the overhead of the algorithm. And if we choose a small K, the algorithm will not get to investigate the effects of changing value of K in depth, and we want to find an algorithm to find an optimum value for K. We would like to investigate the application of ConcurrentHull on dynamic ConcurrentHull problems. Moreover, we want to utilize Convex Hull merging algorithms for the valid partitions. So when we find the Convex Hull for the valid partitions, we can use merging algorithms to merge those Convex Hull with each other instead of finding the Convex Hull again for the whole pruned points. We have introduced ConcurrentHull, a fast Convex Hull computation technique based on pruning unnecessary points. The results show that the ConcurrentHull algorithm can outperform other algorithms on large enough datasets. For example, for 100 million points, ConcurrentHull could outperform qhull by a speedup of 42 times on synthetic data. This approach benefits from discarding of the points that we are certain are not a part of the final convex hull using a highly parallel algorithm. Further, the inherent attributes of the crawlers helps ConcurrentHull to achieve better memory management where other algorithms face memory issues. If you have any questions, please ask in the comments. Thank you for watching.